In this video, we have to find the Fourier transform x of j omega for a time domain signal, which is x of t, which is described mathematically in this expression. Well, it says that x of t is equal to 1 when the absolute value of t is less than t1. Mod of t is less than t1, and it is 0 when t is greater than t1. Mod of t, or the absolute value of t, is greater than t1. So first of all, let's try to draw the function x of t, and then we would like to find its Fourier transform. So let's draw it on the time axis. So suppose this, we have a time axis and we are trying to plot x of t. Here is 0. Now you can see all points towards the right are positive. For example, 1, 2, 3 and so on. All these are positive. Similarly, all points towards its left are negative. For example, this one may be -1, right? -1. Then we have -2, -3 and so on. So these are the values of variable t. Now this function is defined for the by this mathematical description of x of t. So we need to find the absolute value of t. Now you can see the absolute value, as I have mentioned in my multiple times, that you can, if you have a function, for example, you have z, which is a plus j times b, you can find its value mod by just taking the absolute value of this side, left hand side, and that is actually equal to the square root of a square plus b square, right? So similarly, we can write any value of t here on this axis, -1, whether it is negative or positive value. Suppose I take a negative value. Suppose I take a negative value, right? And I assume that suppose t is equal to -1, right? So if I want to find mod of t, I have to find, you can write it -1 plus j0. Now you can find the mod using the same expression, and you would get it -1 square plus 0 square, which is 1. So if I'm interested in finding out the absolute values here, for -1 it would be 1. Similarly, for -2 it would be 2. For -3, the absolute value of t would be 3. And similarly here, I can write all the absolute values of t. Now you can see the absolute values are all positive, right? From 0 towards left or towards right, the absolute value of t are positive. Now come to this mathematical description. Now it would be easier. This mathematical description says that x of t is actually equal to unity when the absolute value is less than t1. T1 is some positive number. So whatever is t1, we can take any t1. Suppose this is my t1. Let me write t1 here. Suppose this is a point t1 somewhere on the positive axis. T1, some positive value. So when this mod of t, if this is t1, so we can also find minus t1 here, minus t1, and all the values on this axis from 0 up to this t1 are the value of t is less than t1, right? All these values of t less than t1. So if we find the absolute value, definitely for 1 absolute value is 1, for 2 absolute value is 2, and similarly for all others. So it means all the absolute values which falls over here, all the absolute values which falls over here are less than t1. So for this period, uh, this signal is unity. So the value is 1 here. I would say 1 on vertical axis. The signal is unity. Similarly, for this range, all the absolute values which are positive, you can say 1, 2, 3, and 4, and so on up to minus t1. All the values are positive, right? So these positive values are also less than the absolute values for this range is also less than t1, right? And sorry, it's not here. For the absolute value is less than t1, which is mentioned here. It is unity. So it means this range, this particular range towards the left of the 0, for which the absolute values, all these absolute values are less than t1, and the signal is unity in this range as well. So the signal is basically 1 from minus t1 up to t1. So we can draw it here. It is unity. And for the rest, when this absolute value is greater than t1, which are all these points and all these points towards the right and the left of the 0, the signal is 0. So we can say this is the signal, right? So this is how you can draw your signal. Let me draw it on a new page, right? I'll draw this signal on a new page and try to solve it now. So let's draw this signal on a new page. Let me draw it here now. I have time axis and this is 0, and our signal is unity from minus t1 up to t1, minus t1 up to t1, and for the rest of the time it is 0. So this is an aperiodic signal. Now we know that we can find the transform x of j omega for this signal, which is defined as minus infinity to plus infinity x of t e raised to power minus j omega t dt. So let's try to solve this. Now you know this one is unity, right? This up peak is 1. Let's solve this integration. We can see that the limits would be only from minus t1 up to t1, because for the rest of this time the signal is 0. So the signal x of t exists only from not from 0, from minus t1 up to t1, right? From minus t1 up to t1, and the signal is x of t is 1 in that period, which is multiplied with the signal e j omega t dt. Now we can solve this integration. It's a simple one, e raised to power minus j omega t over minus j omega with the limits minus t1 up to t1. Now we can consume this negative sign. We can consume this negative sign here by just inverting the limits, and we can write, okay, this is equal to 1 over j omega, and the limits e raised to power minus j omega t, the limits are inverted, minus t1, upper limit is minus t1, lower limit is t1. Just to consume this negative sign, I just replace these, invert the upper and lower limits, right? You can do that. So let's try to solve this equation now. It's easy to solve. Let me solve it. It's a simple integral 1 over j omega. Put these limits, e raised to the power minus j omega, upper limit is minus t1, minus e raised to the power minus j omega, and lower limit is t1. So you can see that this is actually equal to 1 over omega e raised to the power this is j omega e raised to the power j omega t1 minus e raised to the power minus j omega t1, right? Now I can also write this j, I can write divide and multiply by 2, right? I can write divide and multiply by 2, and instead of writing this 2j here, I would write it, I'll just write it below here 2j, and I would erase it from this point. I will erase these from here, right? Now this is actually equal to I'll just erase this one. Let's try to erase these. Now you can see this is actually now why I did it. I did it for the sole purpose of making an expression of sine of omega t1, right? So this is actually equal to 2 over omega sine of omega t1. This is sine of omega t1, or you can say it's basically, if you observe it closely, you can also write it, you just divide and multiply by t1 as well. So you can say 2 over t1, and you can write it as sine of omega t1 over omega t1. In this step I just divide and multiply by t1. Now you are familiar with this mathematical expression that sine of theta over theta is actually equal to sinc function of theta. So using this identity, we can write x of j omega as 2 times t1 sinc function of omega t1. We can write it as a sinc function of omega t1. Now we can draw this function. Now we can draw our Fourier transform, which is just a sinc function, and you know the sinc function from your previous theory. You are familiar with the sinc function, which is nothing but again, if you draw it like this, you can draw your sinc function. You can see your sinc function as a function which looks like this, right? This is actually the sinc function looks like this. We have to see that our x of j omega is actually the sinc function, and but expression is given in this way: 2t1 sinc of omega t1. Now you can immediately find, let me write 2 times t1 sinc function of omega t1, or you can say 2 times t1 sine of omega t1 over omega t1, right? Same. Now you can find some values of this sinc function. You can find some values, some points actually. You can identify some of the points immediately, such as at omega equal to 0. So when you put omega equal to 0 in this expression, you have 2 times t1 sine of 0 over 0, and you are familiar with this sine of 0 over 0. Actually, you are familiar with, you might be familiar with this uh, um, expression, that sine of theta over theta in the limiting case, when theta approaches 0, this term approaches unity. Sine of theta over theta is actually equal to unity when theta approaches 0. So basically this can be replaced with unity, with 1, and when this is equal to 1, sine of theta over theta, this is equal to 1, you are left with 2 times t1 multiplied by a 1. So basically this value, this peak value, is 2 times t1. Now you can also find this null point, the first null, the first 0. This function decreases and you get a 0, the first 0 when your omega, when sine of theta, or when this is 0 actually, when sine of theta becomes 0. So increasing from 0, because if you are now plotting it on omega axis, so when increasing from 0, when your omega t1, in where omega t1 becomes sine of, actually sine of theta becomes 0 when theta is equal to pi, right? When this omega t1 is equal to pi. So when your omega t1 is equal to pi, you would get the first null, or you can say when your omega is equal to pi over t1, omega is equal to pi over t1. So this point, basically this point is on omega axis, it is pi over t1, right? The first null. Similarly, this point is basically minus pi over t1. So omega is pi or minus pi, you would get the null. So usually this is important because this is also known, later on you will see that the first null is important because this defines the main bandwidth of this signal, and this is known as null to null bandwidth. This bandwidth is known as null to null bandwidth of x of t, right? X of j omega. So this gives you the bandwidth of this signal on omega axis, because this is nothing but frequency domain view of because the Fourier transform, so it's a frequency view of our signal. So this is how you you can find the Fourier transform of this rectangular pulse, which is an important signal.